Welcome to my 70-second tutoring session in A-level chemistry. In this video, I'll explain the role of Hooke's law and vibrational frequency of bonds in IR spectroscopy. We have two atoms A and B held together by a covalent bond. Atom A has a mass of m1 while atom B has a mass of m2. And these two atoms A and B, they are held together by a covalent bond, and the strength of this covalent bond is expressed by the force constant F. Now the covalent bond that holds the atoms together is not rigid, but it is flexible like a spring, and therefore the covalent bond, it can stretch and bend. Now when the IR radiation strikes or impinges the covalent bond holding the two atoms together, it tends to induce bond vibrations, and this can lead to stretching and bending vibrations. Now during stretching vibrations, the bond length may either decrease or it may increase. So these are the two possible outcomes when the IR radiation interacts with the covalent bond. Now what is the role of Hooke's law here? Now Hooke's law, it explains the vibrational frequency of the bond that is holding the two atoms together. And using the Hooke's law, one can calculate the region where the probable vibration can occur. And the Hooke's law is given by the equation where the vibrational frequency of the bond is directly proportional to the square root of the force constant and inversely proportional to the reduced mass of the atoms. The reduced mass of the atom can be calculated by multiplying the mass of atoms A and B and dividing the whole thing by the sum of the masses of the respective atoms. Now the force constant, which expresses the strength of the bond, is the major factor influencing the vibrational frequency of the bond. So the vibrational frequency of the bond is governed by two factors. One is the strength of the covalent bond, and the other factor is the mass of the atoms that are held together by the covalent bond. So these are the two factors that governs or dictates the vibrational frequency of the bond, which is holding the two atoms together. Now in the equation, vibrational frequency of the bond is measured in centimeter inverse, while the force constant F, or the bond strength, is expressed in dyne per centimeter, and the mass of atom is expressed in grams. So mu is the reduced mass of atoms linked by covalent bond. That is, it is the ratio of the atoms, ratio of the mass of the individual atoms. Now the force constant is very specific and characteristic for a given bond. So carbon-carbon triple bond is stronger than a carbon-carbon double bond, while the carbon-carbon double bond is much more stronger than the carbon-carbon single bond. So like melting point and boiling points are specific for given organic sample. Likewise, force constant is also specific and characteristic for a given bond. Like in case of carbon-carbon triple bond, a value of around 2150 centimeter inverse is required to induce vibrational transitions, while a value of 1650 centimeter inverse is required to induce the stretching vibrations of carbon-carbon double bond, and a value of 1200 centimeter inverse is required to induce the stretching vibrations of carbon-carbon single bond. So the force constant is very specific and characteristic for a given bond. As the strength of the bond increases, the energy required to stretch the bond also increases. So that is about the strength of the bond or the force constant, which is specific and characteristic for a given bond. Now what about the mass of the atoms? So the mass of the atoms also plays a crucial role in determining the vibrational frequency of the bond. Now the two atoms held together by covalent bond, it could be of same mass or it could be of different masses. Like in case of carbon-carbon single bond, they are of similar mass, while in case of CH bond and carbon deuterium bond, they are of different masses. So let me explain the two parameters that govern or dictate the vibrational frequency of the covalent bond in detail. So the vibrational frequency of the bond is directly proportional to the square root of the force constant and inversely proportional to the reduced mass of the atoms. Now let me explain the first parameter, that is the bond strength, with reference to carbon-carbon double bond, carbon-carbon single bond, and carbon-carbon triple bond. Now the carbon-carbon triple bond is stronger than a carbon-carbon double bond, while a carbon-carbon double bond is more stronger than carbon-carbon single bond. And therefore, as the strength of the bond increases, the energy required to stretch these bonds also increase. As the bond strength increases, the wave number of the IR radiation required to bring about the bond vibrations also increases. It has to be more. So as the bond strength increases, the energy of IR radiation or the wave number also increases in order to bring about the stretching of that particular bond. So as the strength of the bond increases, the energy of IR radiation, that is the wave number, also increases. So a carbon-carbon triple bond can be stretched by shining a IR radiation of wave number 2150 centimeter inverse, while a wave number of 1650 centimeter inverse can induce stretching vibrations of carbon-carbon double bond, and a value of 1200 centimeter inverse can induce stretching vibrations of carbon-carbon single bond. So force constant is a specific and fixed value for a specific bond. So as the strength of the bond increases, the energy of the IR radiation required to bring about bond vibrations also increases. That is to say, with the increase in strength of the bond, wave number required to induce vibrations also increases. So the three takeaway points are: as the bond strength increases, the energy required to strengthen the bond also increases. So it takes more energy or a larger wave number to stretch a stronger bond. And moving on to the second parameter, which is influencing the vibrational frequency of the bond. So let me explain with respect to hydrogen atom and the deuterium atom that is connected to a carbon atom by a covalent bond. Now hydrogen atom is the first element is the periodic table. It is a lighter atom because the nucleus of hydrogen atom, it has a positively charged proton, only one proton, with a negatively charged electron orbiting around the nucleus in its respective shell or energy level. What about the deuterium atom? Deuterium is an isotope of hydrogen. It has a central nucleus that contains one positively charged proton and one electrically neutral neutron, with negatively charged electron orbiting around the nucleus in its respective shell or energy level. So it is a heavier atom as compared to hydrogen. So it is the electrically neutral neutron which is making the deuterium heavier than hydrogen. Now let's see how the difference in mass between these two atoms influences the stretching vibrations of the CH bond and carbon deuterium bond. So in case of the CH bond, so we know that hydrogen atom is lighter, and because of the lightness of hydrogen atom, the stretching of the CH bond, it happens at a faster rate. So there is faster stretching because of the lightness of the hydrogen atom. So in order to match this CH stretching, which is happening or occurring at a faster rate, a higher wave number is required or more energy is required. So around 3000 centimeter inverse wave number is required to match this CH stretching frequency. What about the stretching of the bond interconnecting the carbon and deuterium? Now deuterium is heavier than the hydrogen atom, and therefore the bond stretches at a slower rate. And to match the carbon deuterium stretch, which is stretching at a slower pace, a lower energy is required, and hence the wave number also decreases. So around 2200 centimeter inverse wave number is required to match this slower stretching carbon deuterium bond. So the two important parameters that influences the vibrational frequency of a bond holding the two atoms together are the bond strength or the force constant and the mass of the atoms. Now this is the final equation given by the Hooke's law. Now where did this 1 by 2 pi c come from? That is because frequency is equal to c by lambda, where c is the velocity of light in centimeter per second and lambda is the wavelength of the IR radiation. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.